Okay, let's explore a little bit more this concept of the concentration of hydrogen ions. And it doesn't matter which one it is, but the concentration of one times the concentration of the hydroxyl ions need to add up to this 10 to the minus 14. And I'm going to write it here, just so we don't forget. The concentration of hydrogen ions and the concentration of hydroxyl ions at 25 degrees, remember that, then needs to be 10 to the minus 14. And we have defined what a neutral solution is. We have said, well, we're going to call neutral solutions as solutions that do what water does. And water has this ability that has the same amount of hydrogen ions and hydroxyl ions. And we call that a neutral solution. We compare everything with water and we say, oh, if this is different from water in one way, we call it acid. If it's different from water in the other way, we call it basic. And if it has the same concentration of hydroxyl ions and hydrogen ions as water has, we call that a neutral solution. So neutral solutions are solutions in which you have the same amount, the same concentration of hydrogen ions than hydroxyl ions, 10 to the minus 7, again at 25 degrees. Acid solutions are solutions in which you have more hydrogen ions than you have hydroxyl ions. So what would be more hydrogen ions? Well, remember that this is 10 to the, well, there are negative powers of 10. So what would be a larger number than 10 to the minus 7? Well, a larger number than 10 to the minus 7 would be 10 to the minus 6. 10 to the minus 6 is larger than 10 to the minus 7. In case you want to do it, 1, 2, 3, 4, 5, 6. And 10 to the minus 7 will be 0.1, 2, 3, 4, 5, 7. And 7 is a 1. So, okay, so 10 to the minus 6 would be 1 order of magnitude larger than 10 to the minus 7. So an acidic solution could be a solution that has a concentration of hydrogen ions of 10 to the minus 6, or 10 to the minus 5, or 10 to the minus 4, or 3.27, 10 to the minus 3. They are progressively, going that way in the decimal places. All those numbers are larger than 10 to the minus 7. And we call a basic solution, or sometimes you will see alkaline solution, we use both words interchangeably, is a solution that has fewer hydrogen ions than hydroxyl ions. Again, as in the previous case, in all the cases, both concentrations multiplied add up to 10 to the minus 14, but individually those numbers change. So an acidic solution has more hydrogen ions than hydroxyl ions. A neutral solution has the same amount of both. A basic solution has fewer. So what would be a smaller number than 10 to the minus 7, which would be if it was neutral? Well, a smaller number could be, for example, 10 to the minus 8. Because if I write 10 to the minus 8, 0.1, 2, 3, 4, 5, 6, 7, 8. So 1 order of magnitude smaller. 10 to the minus 9. 10 to the minus 10. So a solution that has a concentration of hydrogen ions which is smaller than 10 to the minus 7, we call that a basic solution. And if you remember from the previous exercise, the calculations we did told us that the concentration of the solution that we were looking at was 10 to the minus 12. That's clearly a basic solution. It's a number much smaller than 10 to the minus 7. So acid solutions have more hydrogen ions than hydroxyl ions. So they are numbers that are larger than 10 to the minus 7. Basic alkaline solutions have fewer hydrogen ions than hydroxyl ions. So there would be a concentration that would be smaller than 10 to the minus 7. And neutral solutions are solutions in which the concentration of hydrogen ions and hydroxyl ions is the same, and it's 10 to the minus 7 because we are working at room temperature, 25 degrees. So that's how we define an acidic, a neutral, and a basic solution. In comparison with, does it have more or fewer hydrogen ions than the water? We call water our normal, neutral. If you have more hydrogen ions, if you are a compound that has more hydrogen ions than water has, we call that an acidic solution. If you have a solution in which you have fewer hydrogen ions than you would have in water, you have a basic solution. So on one hand is the definition of what an acid and a base is. An acid donates hydrogen ions and a base accepts hydrogen ions. And the other thing is what an acidic solution, a basic solution, or a neutral solution is. And when we are looking at acidic, basic, and neutral solutions, what we are comparing is how many hydrogen ions does this solution have compared with how many hydrogen ions water has. And we call water neutral. Okay. The concept is really good, but we are working with very small numbers. We are working with negative powers of 10. That's not easy to work out in a pinch. You know, like somebody gives you 2.27 10 to the minus 3, 0.2 10 to the minus 4, which one is smaller? You need to think about it. Even when I was writing the previous slide, I had to be very careful. What is a number larger than 10 to the minus 7? And I had to stop and write 10 to the minus 6, which for me it was not intuitive. So working with powers of 10 can be done, but it's painful. It's okay now that we all have electronic calculators and scientific calculators. In the 19th century, the early 20th century, it was a real pain. And because they didn't have the scientific calculators we have today. So along comes Sorensen, a Danish chemist, and came out with a scale of pH. Let's say, he said, look, let's not look at the concentration of hydrogen ions. Let's look at minus log in base 10 of the concentration of hydrogen ions. And we're going to call that pH. And why did he come up with this very, very obscure? Oh, let's look at the minus log of the concentration of hydrogen ions. Because if you do minus log in base 10 of a power of 10, a negative one, it will give you a lovely integer, a lovely round number, no round number, a lovely integer, positive integer. So if a solution that has a concentration of hydrogen ions of 10 to the minus 12, if you do the minus log in base 10 of that number, you end up with the number 12. I was like, oh, that's really nice. So the minus log in base 10 of the concentration of hydrogen ions are 3.2, 2.7, 7.8, 10, 12, 14. They are integers that are easier, positive integers. They are easier to work with. So he defined pH as minus log of the concentration of hydrogen ions. He, in parallel, defined pOH as the minus log of the concentration of hydroxyl ions. And if you have a concentration of hydroxyl ions of 0.01 molar, going back to our previous problem, the one we did a couple of slides ago, minus log in base 10 of 0.01 is 2. Again, it's a perfectly easy number to work with. And finally, he converted our equation of concentration of hydrogen ions times concentration of hydroxyl ions equals 10 to the minus 14 at 25 degrees. He converted into this pH and pOH. So pH plus pOH equals 14. So pH minus concentration of hydrogen ions, pOH minus log in base 10 of the concentration of hydroxyl ions, and to keep this condition of experimentally measure there are 25 degrees both concentrations multiplied that up to 10 to the minus 14, pH plus pOH equals 14. And although it does look slightly scarier than if you were just working with numbers, because minus log base 10 of a concentration does sound like perhaps not very intuitive, the numbers you end up working with, 12, 2, 7, whatever, they are much easier to work. So it's much easier to identify at a single glance, looking at a number, if that solution is going to be acidic, it's going to be basic, or it's going to be neutral. That's how he came up with a pH scale. An easy way of expressing, and a very straightforward way of expressing the concentration of an acid or a base, and of telling you how acidic or how basic a solution is. by using the pH minus log of the concentration of hydrogen ions. So we define that at 25 degrees, again, it's all based in this 10 to the minus 14, so at room temperature, a solution that we consider neutral, that has the same number of hydrogen ions and hydroxyl ions, we say that has a pH 7. So pH 7 is neutral. If you have an acidic solution, then you have a solution in which you have more hydrogen ions than hydroxyl ions. So the pH is going to be smaller than 7. 6.9, 6, 5, 4, 3, 1, whatever. If you have a solution which is basic or alkaline, then you're going to have fewer hydrogen ions than hydroxyl ions. And your pH is going to be larger than 7. So from 7.0 something, anything above 7, 7.1, 10, 12, 13, all those numbers that are larger than 7 tell you that that solution is basic. So that is where the 7 and neutral and smaller than 7 in acid and larger than 7 is basic. They are based on these autoionization of water. So that very small number, those very few molecules that are autoionized, reacting as an acid and as a base in your water sample, actually play a huge influence, because the whole concept of pH and what's a basic solution, an acidic solution, and a neutral solution, it is based on that 10 to the minus 14 at 25 degrees. And in this slide, you just have a certain idea of, like you have something like, well, pure water, which is 7, blood and milk that tend to be in the neutral, slightly basic or slightly acidic, to substances that can be very acidic, from the stomach acids to concentrated hydrochloric acid, to substances that are more towards the basic part of the scale, like ammonia or concentrated sodium hydroxide as being, for example, concentrated sodium hydroxide as being a strong base. Okay, let's stop the video and have a little go at these exercises. So would you stop one moment or more than one moment in the video and select which is the correct statement in these two questions? Which of the following relationships is true in a neutral solution at 25 degrees? And which of the following relationships is true for an acidic solution at 25 degrees? Stop the video now, please. Okay. So, a neutral solution. The definition of neutral that we have come up with, that has been come up, is a neutral solution is a solution that has the same number of hydrogen ions, the same concentration of hydrogen ions than hydroxyl ions. So the only correct statement is C, which is the one that has the same number of hydrogen ions and hydroxyl ions. The second question, which of the following solutions, which of the following relationships is true for an acidic solution? Well, an acidic solution has more hydrogen ions than hydroxyl ions. That's how we will have defined what an acidic solution is. And of all those statements, the only one that has that is the top one, A.